the problem says the following. An electric motor exerts a constant torque of 10 newtons per meter on a grindstone mounted on its shaft. The moment of the inertia of the grindstone is going to be 2 kilos times meter squared. Now it says if the system starts from rest, we have to find the work done by the motor in 8 seconds and the kinetic energy at the end of this time. Lastly, what was the average power delivered by the motor? Now before we start, we have to use some formulas that are going to help us solve this problem. Which one of the following is the work being equal to the torque times delta theta, and the torque being equal to the moment of inertia times the angular acceleration. Theta in this case is going to represent the angular displacement. Now, as we solve this problem, we can rewrite the angular acceleration as the torque divided by the moment of inertia. Because we have those two values, we can figure that out. It's going to be 10 newtons per meter over 2 kilograms per meter squared. And that should give us 5 radians squared. Now that we have the angular acceleration, we can solve for delta theta, the angular displacement, which at the end is going to help us find the work with this formula. Now there is a formula that says that the angular position is going to be equal to the initial angular position plus the initial omega plus 1/2 the angular acceleration times time squared. Now as the angular position is going to be equal to 0, we can say that the angular position is the same as the angular displacement. And that is going to be 1/2 5 radian per second squared times 8 seconds squared. Ever since the system starts at rest, this is going to be 0. So as we plug into a calculator, we get 160 radians. Now to find the work done, we just use the first formula that we have up here, and we said the torque, the 10 newtons per meter times the angular displacement that we just found, 160 radians, is going to give us a total amount of work done being 1600 joules. Now to find the average power, we just use the formula work done divided by the change in time. So we have 1600 joules divided by the 8 seconds. That should give us 200 watts. Now to find the kinetic energy, we know that the angular velocity is going to be equal to the angular acceleration times time. So you could say that 5 radians times 8 seconds is going to give us 40 radians per second, which is going to be our final angular velocity. So by using the other regular formula to find the kinetic energy, we just do 1/2 times the mass, the 2 kilograms per meter squared, plus the velocity squared, 40 squared. That should give us 600 joules, which is the same answer that we got for the work done. So in this problem, we got the following. We got the mobile sculpture that is being suspended from the ceiling of an airport terminal building. Then it says that it consists of 2 metal spheres, each with a mass of 2 kilos, connected by a uniform metal rod with mass of 3 kilos and a length of 4 meters. Then it says that the assembly is suspended at its midpoint by a wire, and it rotates in a horizontal plane, making 3 revolutions per minute. The question is to find the angular momentum and the kinetic energy of the assembly. So right here we have the two masses, the 2 kilos each, the rod drawn right here, which is 3 kilos, and then the distance being 4 meters. So as we find the angular momentum, we're going to use the equation L equals to the moment of inertia times omega, or the angular velocity. The kinetic energy is going to be 1/2 moment of inertia times angular velocity squared. So first we have to find the moment of inertia of both the sphere and the rod. So now since we have 2 spheres, we can say that the radius is going to be the following. There's a distance from one sphere to the center of the rod, and one distance from the sphere to the rod. So we have a radius of 2 and 2 meters. So the moment of inertia of the sphere is going to be the mass times r squared. And r in this case is going to be half of the distance. So we square that up and we say the 2 kilograms divided by the 2 meter square is going to be equal to 8 kilograms per meter square for the moment of inertia of the sphere. For the moment of inertia of the rod, we use the formula that is on the last page of the worksheet. So it goes like this: 1/12 times the mass times the length of the rod squared, and that is going to give us 4 kilograms per meter squared. Now to find the total moment of inertia, we have to multiply the two masses, so it's going to be 2 times 8 kilograms and add it up to the moment of inertia of the rod. And that should give us a total amount of 20 kilograms per meter squared. Now to find the angular momentum, we first have to convert the angular velocity from revolutions to radians. And that is what we did up here. We cancel out the revolutions, cancel out the minutes, and we get 0.31 radians per second. Now we can go ahead and use the formula that we set up in the first place. We got the moment of inertia times the angular velocity. Total moment of inertia times the angular velocity should give us a result of 6.2 kilograms per meter squared per seconds as our angular momentum. Lastly, the kinetic energy is going to be 1/2 times the moment of inertia times the angular velocity squared. So it's going to be 1/2 times 20 kilograms times meter squared times 0.31 radians per second squared. And the answer would be 0.86 joules for the kinetic energy. So we got kinetic energy and angular momentum.